Welcome back, class. So we were learning about the operation of the synchronous generators, and now we are starting a new topic, which is parallel operation of AC generators. So practically what is actually happening, that you don't have only one generator which is actually supplying to the load. Okay, so usually we have multiple generators which are actually operating in parallel to meet the load requirements. So for example, you could have more load requirements. Okay, for example, let's say you have a load requirement of 2000 watt. Okay, and this generator can supply, let's say, 1500 watt, and this generator can supply, let's say, 500 watt. Okay, so basically load requirements will be met by the two generators. Similarly, we can install many generators which will be operating in parallel. Now we are going to study that if the generators are working in parallel, so how basically they work. Okay, what is the mechanism? For example, if you want to attach a new generator to your already running system. Okay, so there is a switch. Okay, there are three-phase system. So these three phases must be connected here. Okay, so that if this generator is supplying 1500 watt, this should supply 500 watt. Okay, so the total load requirement should be met. Okay, but there is a fixed mechanism, there is a rule, there are rules which we should comply before attaching the new generator to the existing system. Okay, so what are these rules that we will look now? Okay, now basically there are multiple advantages, like you can meet more load requirements, okay, with the parallel generators. Okay, your system will be more reliable. Okay, it means, for example, if one generator needs maintenance, okay, so you can remove that generator from the system and you can do the maintenance, and rest of the generators, okay, they will supply the required power. Okay, so these are the multiple different advantages. Okay, now the rules are, if you want to attach a new generators, okay, so before the attachment you have to ensure that the RMS line voltages of the two generators must be same. Okay, so whatever RMS line voltage you are getting here at these points from this generators, okay, so RMS line voltage, okay, so this generator, it should also have the same line voltage, because you are connecting these terminals at these loads, so they must have the same line voltages. Okay, this is the number one rule. Okay, second rule is the two generators must have same phase sequences. Okay, you have three phase. For example, the first generator, it has a sequence of ABC, like voltage A, voltage B, and voltage C. Okay, this is ABC sequence. Okay, now the second generator, it must also have the same ABC sequence. If, for example, the second generator has this sequence A, C, B, like this is phase A and this is phase C and this is phase B, so this has a different phase sequence. Okay, so what will happen now, if you attach that, so the current on this phase and this phase, it will remain same. Okay, but the currents on these phases will be different because of the different phases, so it will affect the generator performance. Okay, the third thing is the phase angle of the two phases must be equal. Okay, for example, if you are supplying VA with a phase angle of 30 degree, so this second generator, same phase should have same voltage, should have the same phase angle. Okay, so the phase angle must be same. Okay, and the last very important condition is the frequency of the new generator. Okay, so like you have generator 1, you are adding the second generator, so the frequency of the new generator, which is also called oncoming generator. Okay, for example, if this generator is operating at electrical frequency of FE1, then this generator electrical frequency F2, it must be slightly higher than the frequency of the running system. Okay, so this must be higher than the already running system. Why? It will help us to adjust the phase angles. Okay, we will see that thing in more details in coming slides. Okay, so basically, if this frequency is higher, we can easily adjust the phase angle, and then when both systems are combined, they will be actually operating at a combined system frequency. Okay, we call that system frequency. Okay, we will see that like if two generators have different frequencies, then how we can actually calculate the system frequency. Okay, so these are the rules which must be met. One very important thing which will happen when we actually connect the two different generators. Okay, so basically our target is that our power must be same. So we know that power is basically the input torque multiplied with the angular velocity, right? And we want to ensure that the torque, okay, which is actually becoming the cause of the conversion of the mechanical power to the electrical power, that torque is basically being produced by the prime mover. Okay, so torque must be constant. Okay, so if torque is constant, okay, and now if the power drawn from the prime mover increases, so if you need more power now, okay, now to make this equation, okay, to ensure that in this equation torque is constant, so now if you are increasing the power, it means you should decrease the velocity, angular velocity. Okay, so that is the very important relationship, that when the power drawn basically increases, so the velocity must be decreases. So usually this relationship is non-linear, but we assume the linear relationship. So what does this mean? This mean is, for example, let's say this is our power, okay, and now my generator is working, okay, at the no load condition, and it has a speed of n, okay, which is the no load speed, okay, angular velocity. This is radian per second, and we can go to the revolution per minute, okay, rpm. Now if the power requirement is increasing, so we will have the decrease in the speed, we will have the decrease in the angular velocity speed. Okay, so speed will be drop. Okay, for example, let's say if the new power is p1, so now your system will be operating at this frequency, okay, that is the full load, okay, frequency speed. Okay, so that is the relationship. So we will have the speed droop. Okay, speed droop of a prime mover is defined by the no load speed divided by the full load speed, okay, divided by, so is there subtraction, no load minus full load divided by the full load. Okay, so usually the speed drop is 2 to 4%. Okay, and we also know that very well that basically we have a relationship between electrical frequency and the mechanical electrical frequency and the mechanical speed, right, and p over 120. Okay, so basically electrical frequency is directly proportional to the speed. Okay, so if we can also draw the relationship between frequency, that we have a no load frequency, and when the power is increasing, we will have a drop in the electrical full load frequency. Okay, so that will be the relevant frequency graph. Okay, so this is very important thing. So these are the two graphs in more clear form. So when power is increasing, okay, speed is decreasing. Okay, so we get a full load speed. Similarly, frequency, we will get the full load frequency. Okay, now these basically frequency power characteristics are very important. Okay, this is very important in the parallel operation of the generator. So based on this, we can actually write this very important expression, that the relationship between frequency and power, it can be represented by using this formula. This is very important formula for the operation of the parallel operation of the synchronous generator. So this formula is here we have the no load frequency, we have the system frequency. Okay, that what is the frequency, that when you attach a load or the power requirement are increasing or decreasing, then what is the change in the system frequency, basically what is this frequency. Okay, and like this is the no load frequency. Okay, and then we have SP, which is the slope of the curve, that by which factor, okay, we are actually having a decrease in speed or decrease in frequency. So what is the slope of this linear curve, that is called SP. Okay, so this is very important relationship. We will see the relevant example about this relationship in the live session. Now let's say usually there are different kind of loads. Okay, like if we have infinite bus, okay, and you are attaching a new load to that. Infinite bus is basically a power system, okay, which have very high power, okay, infinite power. Okay, So basically now if you're attaching a new load, okay, let's say a new load of 1000 watt. So now the total power basically will be infinite plus 1000, which will be basically infinity. Okay, a very large power. There will be almost no change in the total power. Like if you attach some load, okay, or if you subtract some load, okay, so the net power, because this is an infinite bus, there will be no major change in its power. So when there is no major change in its power, this means there will be no change in its electrical frequency. So for the infinite bus, our graph of the power frequency relationship will be look like this one. There will be no change in electrical frequency. Okay, similarly there will be no change in the terminal voltage of the generator. Okay, so in this graph, if we see that, so this is basically the positive axis of the power, this is the negative power. So if we are having more powers here, if we are adding more generator here, so basically here we have the positive power. So positive power means basically you are supplying the power to the system. Okay, your new generator is basically supplying the power to the system. And if your power, connected power, is coming here, so here we are having basically negative power. So basically your new generator will be consuming power. It will be taking power from the system. It will not be supplying. So basically real power has a relationship with the frequency. And if you talk about reactive power, okay, similarly positive reactive power, it will be supplied, and negative reactive power, it will be consumed. Okay, so reactive power basically have a relationship with the terminal voltage. Okay, so these are the things which you must focus here. Okay, the real power has a relationship with the frequency. Okay, so typically we can draw, like if we have for example infinite bus. Okay, so this is basically the bus which is supplying infinite power, and now if you are attaching a new load, okay, so if you talk about infinite power bus relationship, so power and the frequency remain constant, right? So basically that is the line for the infinite bus. Okay, now you are attaching a new load. Okay, so that is the new generator, sorry, not load, new generator characteristics. Okay, and we know that basically now if you notice here, this new generator, okay, its frequency, okay, it's higher than the no load frequency of the system. Okay, you are attaching it at a higher frequency. Why? Because if you attach it at a high frequency, now this line and this line will intersect, so that will basically become your system frequency. Okay, so if we attach at a high frequency, then we can easily adjust, okay, these two. Okay, so this is the power of the infinite bus, and that will be our generator power. So total load power basically will be sum of this power, infinite power, plus the generator power. Okay, now what will happen, for example, if you are attaching a load, okay, which no load frequency less than your system frequency. Okay, it means you are attaching a load which is coming here like this. Okay, so in this case basically what is happening, okay, now you are getting a negative power. Okay, so that will be their intersection point, so that will be your system frequency. So now for that system frequency, basically your generator power is becoming negative. It means your system is working as a motor. Okay, your generator is basically consuming the power from the infinite bus. So this is this relationship. Okay, basically this is called as housing diagram. Okay, this is called house diagram, and the same thing goes for the terminal voltage, okay, and the other characteristics. Okay, so we will see the relevant example and more details about this in the live session. Thank you very much for your time here.